Hey guys, so this is my video submission for Physics 2211 Lab 3. I'm Rishi and let's get into the lab. So for the lab overview, this lab focuses on analyzing the trajectory of a star orbiting a black hole to estimate the black hole's mass and simulate a spaceship's flight in its gravitational field. We aim to calculate the black hole's mass and determine the initial velocity required for the spaceship to safely navigate without crashing. So we had a couple of concepts, but I'm just going to discuss three of them. For our models, we utilize gravitational models to simulate the motion of a star orbiting a black hole and the dynamics of a spaceship navigating the gravitational field. And our three concepts were one, Newton's law of gravitation. So masses attract with the force inversely proportional to the square of the distance between them. In class, we talk about G m1 m2 over r squared, and we had to use that equation a lot in the GlowScript code. Second, we talked about momentum and its changed. In class, we learned that the force on an object is equal to its change in momentum over the change in time for dp/dt, and this is found a lot in our VPython code. And three, it's multiple gravitational interactions. Because there are multiple planets in the system, there are multiple gravitational forces, and we had to account for that. An overview of the main result. So in this lab, we found the estimated mass of the black hole based on the star's trajectory and the initial velocity needed for the spaceship to safely navigate its gravitational field. Before we get into these three slides, let's talk about what actually we did in the lab. So initially, we analyzed the star's motion to find the net force on the star for all points in the data. And we use the results of the analysis to estimate the mass of the black hole. So I was able to do this inside of my code. Here you can see I've generated this orbit, and I was able to find the mass of the black hole at 1.64 times 10 to the 34th kilograms. Um, Second, with lab instruction part 2, don't crash. This one provided a sample scenario where we're in a spaceship approaching the system that we just simulated, and as we get closer, we notice there's a planet orbiting the black hole, much closer to the black hole than the star is. They also gave us these conditions and asked us to use a GlowStrip code with entering the mass to determine the initial velocity. So we did this in part 2. Here we determine the distance um, that the we said the distance that it is after 60 minutes. So the ship's now 1.6 times 10 to the 10th meters away from the event horizon of the black hole. So after this, we're going to go into the two what does it mean questions. So the first question asks, in your analysis, you should discuss how the net force and its parallel and perpendicular components are different from the rate of change of momentum in its parallel and perpendicular components. So I'm going to answer that. So first of all, the net force of the star, which can be broken down into parallel and perpendicular components, reflects the gravitational pull from the black hole, but in the rate of change of momentum indicates how the star's momentum varies due to these forces, influencing both its speed and direction. Keep in mind this also kind of goes along with F is equal to dp over dt. The rate of change of momentum talks more about how the forces on the actual object. Um, for the second question about the actual observable measurements, net force can be quantified through gravitational calculations and accelerations, which allows for the direct observation of its effects on the star's trajectory. The rate of change in momentum can be measured through the star's velocity changes over time, which provides insights into how external forces can impact the motion. Our other question was a what if question. It said, instead of wanting to take a look at the black hole and leave, you decide you want to enter into the orbit around the black hole. What initial velocity would your spaceship need to have in order to enter some kind of planet in the black hole? And to do this, you're gonna have to set the force equal to you're gonna have to set the centripetal force equal to the gravitational force. So to enter into a stable orbit around a black hole, the spaceship must achieve a specific initial velocity that balances gravitational attraction centripetal force. This velocity can be calculated using the gravitational force equation. So basically what we do is we take g m1 m2 over r squared and set it equal to mv squared over r and solve. Now I'm going to talk about the similarities and differences between the two models and possible sources of error. So for the gravitational model, this model was used to analyze a star's motion around the black hole, and it assumes a gravitational interaction where only the only force acting on the star is a gravitational pull from the black hole. But in contrast, the model for the spaceship's navigation incorporates multiple gravitational forces, including those from both the planet and the black hole. I also want to talk about some measurement uncertainties. Errors in measuring the distances can significantly impact the calculation of the gravitational forces. So if we made some mistakes there, it could have led to some inaccuracies in the black hole's mass or the required initial velocity, and some assumptions in the model. The simplifications made in the models, such as ignoring the effects of other potential bodies or assuming a perfectly circular orbit, could lead to some differences between the predicted and actual trajectories. Thank you, guys.